Hi everyone, this is Jake Fry, and today I'm going to talk about position, displacement, and time. This is the third video in my video series on Intro to Mechanics, but it's the first one which we could say is definitely in the realm of physics, which is great. Just as a warning, it will use ideas in my previous two videos on defining coordinate systems as well as how to use them in vectors. So just to be warned. Alright, so physics is all about describing motion. And typically, to describe the motion of an object, the most basic way to do this is just to determine where the object is, which is the position, and when it was there, so just the time. And so we can do that without using mathematics to get a rough idea of what's happening in the system by using something known as a motion diagram. And these are just ways to show the object's position at equally spaced distances of time. And so the way that I think about this is that I have a movie film. So each still shot is of course taken by the movie camera at a set equal space and time. So if something's moving, we know that we can count on the time always being equally spaced. So if we have 4 different frames of that movie and they're equally spaced, such as the skateboarder, we know both equally spaced in position as well as equally spaced in time means that the skateboarder is moving with constant speed. If instead we have 4 different frames that are closer together at the beginning and then further apart as time progresses, we know that the object is speeding up. And inversely, if they start more separated and get closer together, they're slowing down. So this is a great way to visualize in your head how to describe motion without using complicated coordinate systems or vectors. So now, to make it more mathematical. So, in physics, we care a lot about simplifying the system as much as possible. So, ideally, every single object would be a point particle. But of course, this isn't always the case. So, what do? So we try to make it a point particle. And we actually use something known as the center of mass of an object to do this. And I'll describe what the center of mass is in a later video. So, the reason for this is if we wanted to apply a coordinate system onto the motion of an object, how would we know where to put the position coordinates of the object? So like in this case with this diver, they start stretched out, they start rolling around, and it's very difficult to see where to put a position coordinate for this location versus the one at the end. And it turns out using the center of mass, which is very close to the belly button of a human, is a great way to describe most of the physics. In fact, it describes quite well all the translational motion in this case. And translational motion is anything such as projectile motion, which is like this, which takes a parabola type shape, or throwing a baseball. Linear motion, such as the car in the motion diagram I showed before, that's just in a straight line. Circular motion, such as the moon orbiting the Earth. Those are all translational motion, where tracking the center of mass is great. However, you do lose information about the rotation, which is obvious from here. So we can see that we can track that center of mass position, but we're losing information about what happens during the diver's flip. So, but in physics we like reducing everything to the minimum amount of information that we're trying to describe, and then we'll add on more information as we get more complicated, I guess. Okay, so now that we have a point located at the center of mass of an object, how do we describe the absolute position? So to do this, we use an applied coordinate system. This gives us a reference frame to be able to give position coordinates, in the case of the diver, in two dimensions, say x and y for horizontal and vertical position, for each location of the object throughout its motion. Okay, so in our case with the diver, I could put this X and Y axis with the origin right on the diving board and create a grid system, and so we can find the position coordinate for each of these center of mass points. And so of course, even if it goes below 0, we can still use it. So yep. And so then you might be like, okay, so we have positions, but what about the position vector? So remember when I talked about vectors, it gives us both a magnitude and a direction. And so we can do that here as well. It's a little bit weird when talking about position vectors and how that's different from a position coordinate, but in fact it is. So yeah. And so we can have position vectors for each of these locations in the object's motion, as shown by each of these colored arrows, to describe the motion. Okay. And now time. How did we deal with time? So time is arbitrarily assigned to each position, typically with time equal to 0 at the beginning of the motion. And so in non-relativistic mechanics, which is what I'm pretty much exclusively going to be talking about in the next many videos, time is not included within the vector itself. So I'm not doing something like, oh, one of these position vectors is x, y, and ct, speed of light times time. So yeah. So one way to deal with the time is by using another perpendicular axis to the coordinate system. So in one dimension, if my position vector is x in meters, I can track the position. So it starts at 1, goes up to 3 in 4 seconds. And so I can have a horizontal axis where this axis is time in units of seconds. So that's one way to put time into the system. Another way is to create a, sorry, my little face is in the way. Another way is to attach the time to each reference frame. And now I'll go a lot more into detail with what I mean with reference frame, but basically what it is I have one coordinate system at time t equals t, where the origin is somewhere here, and I have variables, this time in 3D, x, y, and z. And then at some later time, t equals t prime, I have the origin shifted to the origin prime, x prime, y prime, and z prime. So that's another way. So this is actually a much more useful way when dealing with things like invariance. And I'll probably use this one more than using a separate axis for time. Okay. And then the third way is having time be implied by using motion diagrams. So like the original diver is equally spaced in this case, using motion diagram, having the time be implied. Okay, so now on to displacement. So we've pretty much set up our problem. We have position vectors, we have time, but now we want to do things with them. So displacement. The displacement is the change in position vector given by delta r. So if we have r1 is our first position at point p1, and after some time our position goes to p2, described by r2, then we can use vector addition to see that r1 plus the displacement vector delta r is exactly equal to r2. So we could use algebra to see that the displacement would just be r2 minus r1. Great. And now, what's the difference between displacement and distance? So this is why it's very important to use vectors for our position, because distance and displacement are almost always different. So the total distance between 2 points, say this is P1 and this is P2, the total distance depends upon the elaborate path that you take. while the displacement between P1 and P2 is just the difference between the initial and the final vector. So a lot of problems that you'll see will be things like, oh, I start walking at 50 miles north and 30 miles east. What's my total distance and what's my total displacement? And those are two different things. But the way that I think about this is that whenever you're talking about like distance and displacement, is that your distance is what the path that you would actually take in order to reach from point A to point B. So like if you wanted to go, I guess, from, let's see, a place with mountains. If you go from Denver to Boulder in Colorado, you know that there's lots of mountains and hills in the way. And so the distance would be you crossing over all of those hills, while the displacement would be what a bird would do. It would just fly from one point to the next. So that's kind of the way that I see the difference between distance and displacement. And you might say something like, oh, well, birds can't go underground. but just go with the same idea, no matter which direction you go. Okay. And now on to time intervals. So this is very similar to displacement, except time we know is a scalar. So if we go back to our original example, between P1 and P2, we have our displacement delta r. Similarly, the time interval is just given by delta t, where the time t1 is when the particle is at P1, and time t2 is when it's at P2. And so t2 is just equal to t1 plus delta t. So your time interval is just the final time, t2 minus t1. And so the reason that I describe both displacement and time interval is that different observers of the same motion, they may end up using a different coordinate system. So they could use spherical coordinates while someone else is using Cartesian coordinates. They could also use different clocks. So maybe one is a minute faster than the other. But when you take the displacement and also the time interval, both of those quantities will be identical. So it won't matter if you have a different clock or a different coordinate system. And so this is the last slide. So this is very important because you might be worried if you use a different coordinate system that you'll get a different answer in the end for your problem. That's not the case. And so your goal is to basically find what is the easiest coordinate system to use to do all the mathematics. Because you'll know at the end of the day that you'll get the same answer even if you use a much more complicated or cumbersome coordinate system to use. All right? And yeah, thank you for listening. And if you have any questions or if you want any examples on how to use things like displacement or time intervals, just write below in the comments, and don't forget to subscribe for some more intro physics, or in particular intro mechanics. All right, thanks.